Hi, my name is Tony Gibbs. I'm a Principal Database Solution Architect here at AWS on the Amazon Timestream team. And today I'm going to be taking you guys through a deep dive on Amazon Timestream. So we're going to get started just by going over a little bit of introductory material. We're going to then move on to some architectural concepts, go through some of the terminology that's in Amazon Timestream. We're going to then go through data storage and a deep dive into the ingestion and best practices and that sort of thing. Then we're going to finish up on some query processing. I'm going to give you some additional links and places where you can get further learnings, that sort of thing, to wrap everything up. And then that's going to be the session for today. So normally I always like to get a feel for where everyone's at in the audience. Obviously, this year it's virtual. So I'm going to make some assumptions here on where you guys are at. Because Timestream is a relatively new service, I'm going to make an assumption that most of you actually haven't used Amazon Timestream yet. But I am going to make an assumption that you guys are, database professionals, that you're probably used to using, say, like relational databases, maybe some NoSQL databases or data warehouses, and that sort of thing. You're probably comfortable reading SQL, reading through Python. So we're going to have some Python and that sort of thing. And so I do make assumptions that that'll be things that you'll be comfortable at least reading through. So let's first start out what you use Amazon Timestream for. The first thing is where we've really seen a lot of customers adopting Timestream is in the IoT space. We have a lot of customers that are sending in telemetry data from sensors, and this data is usually coming in a lot of times real time. Sometimes it can be semi-connected, where there's intermittent access and the data comes in batches. But it's about like measuring sensor data, whether that's temperature data or maybe even sensors from a car, for example, measuring things like the speed or how much fuel is left, that sort of thing. The next one is DevOps data, and this is like maybe an application that might even be running on AWS. It could be comprised of hundreds of EC2 instances that are all sending in telemetry data, how much CPU is being used, how much memory, your disk usage, that sort of thing. And you're sending that in and you're monitoring health metrics and that sort of thing. The last one is a bit of a catch-all, and that's what we call kind of app analytics or app analysis. And this might be, things like Clickstream, for example, or maybe even something like an application like video analytics, for example, where you're, measuring, what the average bit rate is while an end user is watching a show, and you're watching, keeping track of when the videos are paused, maybe when they stop watching it, and you're all that kind of thing. And so it's really kind of the catch-all, and it requires a little bit more analysis on whether or not it's going to fit well into Timestream or not. But these are the three main use cases for Amazon Timestream. So traditionally in the past, before we had Timestream, you probably would have put this data into a relational database. It's kind of the catch-all bucket. You weren't sure where to put it, and you just put it in there. There are some challenges with this. Obviously, relational databases, they don't always scale to where we need them to, especially in analytics workloads. They typically are scaled vertically, most relational databases. And the other thing is you have to define a schema up front. So you'd be, typically doing like a create table statement, and you define, some columns with various data types and that sort of thing, and then you'd roll that out and you'd send out your sensor, and then, hopefully that all works well. And then you might end up having like a new version of the sensor that ends up going out. And, you're going to end up having to go back to that table, and you're altering the table, adding a column, or maybe you're changing some data types, that sort of thing. And while it's not like incredibly complex, it can be a lot of extra work just to kind of keep all these things in sync and coordinated. Then moving a little bit closer towards the existing time series solutions, there are some of them. And there's tooling for some of these, whether it's ML tooling or whether it's tooling that is meant to send data into time series like databases, and that tooling might not work for a relational database. So those are some of the existing challenges with those solutions. With the existing time series solutions, so there are a handful of them that exist, what we've heard from customers is that they can be difficult to scale. It's a lot of maintenance. You're setting up clusters. They may not scale to what you need them to, so then you start offloading data out of them, maybe putting it into something like S3, but you want to continue to query that historical data, and you're kind of mixing multiple database systems together to kind of really meet your time series needs. So these are some of the difficulties that we have heard customers telling us about both relational and existing time series solutions. So this is where Timestream comes in. It is a serverless database. So that means there's nothing to manage. There's no clusters to provision. There's no instances to pick or any of that sort of thing. You just create a table and you just put data into it and you query that. There's absolutely nothing to really configure except the length of time that you want to retain data. And we'll talk a little bit more about that in a couple of slides when we get into the various storage tiers that Amazon Timestream supports. The next thing is Timestream is designed to scale automatically behind the scenes, and it's meant to scale all the way up into trillions of events being ingested in a Timestream every day. The query engine is also scalable, and we'll talk about that when we hit the architecture on why these things are scalable and how they're all separate. Timestream is also designed to support SQL. We wanted to make it easy to use. We didn't want to have you learn a new querying language or anything like that. So it's pretty much ANSI SQL. And we have layered in on top of that, interpolation functions and that sort of thing for gap filling. They're typically common in these time series use cases. Then obviously security, number one at AWS, and everything in Timestream is encrypted. It's not even by default. It's just always encrypted, both in flight and at rest. So let's go into being this serverless database. This means that we're continually rolling out features as we go. So we launched Timestream in September 2020, and through that time since then, we have continued to roll out new features. And so these just are on a continuous basis. There's no maintenance, there's no cycles or anything like that. There's no downtime when we do this. Timestream actually has 4 nines SLA, so 99.99 availability. So the first piece of terminology introduced you to is tables, and then within the tables we put in records. There's no data definition required at all when you create a table. You're just giving the table a name, and we put these records in. And then, like I mentioned earlier, the only thing that we actually define are the retention policies on our storage tiers. And we have 2 storage tiers. We have both an in-memory tier and a magnetic tier. Each of these tiers are responsible for different things, which we'll talk about a little bit later. But you do have to have a retention time period for each of the tiers. So in the in-memory tier, you have to have a minimum of 1 hour retention period. And on the magnetic tier, a 1-day retention period is the minimum. And then you can modify that up. The nice thing is these retention time periods can also be modified after the fact. So you can start out with one retention period, and you can later, as you're using Timestream, you can adapt these depending on your requirements. So going into the Timestream architecture, I'm going to focus on the diagram here on the right here, and not so much on the text on the left. And I'm going to start at the top. So there's this Timestream Write SDK, and there's actually on the bottom, there's a Timestream Query SDK. And they're almost like 2 different SDKs, and you'll notice them being separate even when you're using the AWS CLI. So going from the top down here, the Timestream Write is you're going to use that to send data into Timestream. And underneath, that's going to go into our ingestion layer, which is highly scalable, and it will scale as you send data in. When you get the 200 OK back from the SDK, that means the data has been safely written across multiple availability zones multiple times, and then we're going to then replicate that data down into our in-memory tier. Now, depending on how you've configured the memory store retention period, when the record hits that retention time period, we're then going to move the data over into our magnetic store, and we're going to store it there. Now, our query layer, which you can see down at the bottom, when you send a query up to Timestream, what's going to happen is that query layer, which is also highly scalable, will auto-scale out. It knows where your data resides. And so you don't need to do anything to tell Timestream, hey, this data is in the in-memory tier or the magnetic tier or anything like that. The engine is smart. We call it an adaptive query engine, and it'll figure out where that data is. It'll get the answer back out of whichever tiers it needs to and out to you through the Timestream Query SDK or JDBC driver. So dimensions are the next piece of terminology I'm going to introduce you to. We support up to 128 of these. These are defined at ingestion time. So as you're writing data into Timestream, we're going to dynamically figure these out. You're going to define, hey, this is a dimension, and you're going to send that in, and we're going to add them as necessary. The next piece is measures. So we support up to 1,024 measures within a single table. These are, again, also added dynamically as you're adding data in. These do have a data type that you define. Typically, the usual ones are big ints and doubles. In certain cases, it may make sense, like if it was a health check, for example, for it to be a Boolean. In other cases, maybe you're saving lat long or something like that, and you need something a little bit more dynamic. You might store something like that in as a varchar. But the important thing is that these are added dynamically as well at ingestion time. The next is time series. So this is what we're typically expecting data to kind of come into Timestream as. So this is a series of data points. So you think of this as you have this set of dimensions, and then for that set of dimensions, you have a measure value that's changing over some interval of time, and that's really what it is that you're measuring. And it's kind of hard to explain verbally like this. So what I'm going to do is I'm going to have this slide here that I'm going to go through and kind of explain. So you can see on this is actually DevOps data inside this table, which is represented in Timestream. And you can see these timestamps going down, and you see this measure name, which is CPU utilization. That goes to mem utilization and network bytes. In Timestream, this would be one of the series, for example. So you can see the CPU utilization in time, and as the value is changing over time. And that's what a time series is. So that might have made you ask some questions about the data modeling side of things. So I just want to kind of cover this. The same record, this is a CPU utilization, that same first record here. And this might be how you'd be modeling this in maybe a traditional relational database. So you can kind of see like the time there, the region, that sort of thing. And you see the CPU utilization, memory utilization, network bytes. In Timestream, the way that we unpivot and model this data would be something like this. So you can see here, we have the timestamp down on the left, and we have the measure name going down. So the data has been kind of unpivoted out of the table or from one format into the other. So this bottom way is how we represent all data in Timestream. And what that really means is that there's a single measure for every record in Timestream. So some characteristics of data that we're storing in Timestream. Obviously we talked a little bit about this one measure per record piece. The next is deleting and updates. We don't, this is mostly a pen database, so we don't delete data in Timestream. We do, however, support updating a single measure. So if you have like a single value that for a set of dimensions before it, and you just kind of overwrite that. The default behavior is we reject duplicate records, but you can also do an update or an upsert, I guess, on that measure value. So that would be the only real kind of mutatability that we support in Timestream. The last is that Timestream is designed for handling real-time ingestion. You don't have to ingest it in real time, but it is designed for high-speed real-time ingestion. So let's move into data storage here, or data ingestion first. We're going to go through ingestion, and then we'll touch on the storage piece here. So in the data ingestion side, you're typically ingesting data through various SDKs, Java, Python, that sort of thing. And it's going to feel a little bit like writing data in using something like, if you're familiar with DynamoDB or Kinesis, it's going to be a bit like that. We also have native support with the AWS IoT core. We also have an adapter for Kinesis Data Analytics for Apache Flink. And then we also have an adapter for Telegraph, which are two other common ways of sending data into Timestream. So I'm going to touch on the pricing here. Pricing for Timestream in US East 1, 2, and US West 2. This is 50 cents for every 1 million 1 kilobyte records. You wouldn't normally probably go through counting all the bytes and that sort of thing in the records, but I'm just going to walk through this exercise here, just counting bytes and how the pricing works and how you can optimize pricing, and then touch on the best practices. So we have the single record here. It's a CPU utilization, and I've expanded out the time into an epoch timestamp, because that's actually how you send data actually into Timestream, and that's a nanosecond timestamp. You might pick something less granular like seconds or milliseconds or something like that, but that's a nanosecond timestamp. And if we were to send this in a Timestream, it would be 8 bytes. And it doesn't matter the length of that. That's just what we build for, so you can send whatever type of timestamp you in. Then the first dimension here is going to be the name of the dimension, which is region, and US East 1. And if I were to count up these bytes, it'd be 15 bytes. Going on to the second dimension, we'd have 4 bytes, one for AZ, one for 1D there, so the concatenation of those. And then you can see I'm just going to kind of go through here. And the measure name is going to be, in this case, CPU utilization, and that would be 15 bytes. And then for the measure value, this would be 4 bytes, and that would be the string representation of 35.0. The total bytes here would be 79 bytes, and that would be what this record would cost to send into Timestream. So I'm going to build up a scenario. I just added an extra record there just so you guys can visually see that there would be many of these records. In the scenario, I've kind of made it up so that there's 100 measures we're going to send in. And we're going to, let's just say that we have a single EC2 instance that's sending in this DevOps data every 5 seconds. And I know the last record was 79 bytes, but let's just make an assumption that the average record is 110, and maybe we have some longer names and that sort of thing in here. And we'll just say 110 bytes per record. So if we were to send this in a Timestream, you can see it. I've kind of hard-coded this into the Python here, these values. Obviously, we'd build up the variables and that sort of thing for these records. I'm going to build up the first record for CPU utilization. I'm going to send that. You can see I built it up for memory utilization. I'm going to do the write records request and send that. And I do that over and over again for all of the 100 measures. If I were to price this out, what would end up happening is I'd have 100 measures. That would basically mean 100 writes in Timestream. If I further expanded this out over the 12 writes per minute, because we're sending this every 5 seconds, we'd have 1,200 writes. Over the hour, we'd have 7,200 writes. Over the day, 1.7 million. And over the entire month, you'd have almost 52 million writes. And this would correspond to almost $26 to send this data in as is to Timestream on this regular basis for the whole month. Now, this is just a recap of that code. You can kind of see what I had there, and I think we can do quite a bit better. Well, I know we can. And what we're going to do is we're going to change this code. You probably notice that the command is called write records. And what I've now done is I've changed this code so that I'm putting all of the values into a single list, in this case records, and we're going to send all 100 of these measures as a single request to Timestream. And this is going to greatly reduce the amount of data that we're kind of sending in these small little pieces. If I were to redo this pricing, in this particular case, I have this 100 measures that's going to correspond now to 11 writes, since we have 11 kilobytes of data to send in. It's going to be 132 for the 5 minutes, almost 8,000 for the hour, and expanding it out, we have 5.7 million writes for the month, which corresponds to $2.85. So you can see that's a pretty huge reduction in price, going from $26 down to $2.85. Just looking at this code one more time here, if you look down the bottom right of this code, you're going to notice there's this empty dictionary being sent into the common attributes argument here in this call. And you probably notice that there's quite a bit of redundant data on the screen. We're kind of sending in this timestamp multiple times, this dimensional data multiple times. It'd be really nice if we could reduce the data sent there and kind of take out that redundancy. And we can. So I'm going to rewrite this, and you can see now I've introduced this variable called common attributes, and you can see in there that I have this timestamp value. You can see in there all of the dimensional data, and then we have the records down below. And so that, I believe, counting that out, you should see about 19 bytes for that first CPU utilization and 22 bytes for the memory utilization. And we're going to basically, each of the records now is significantly smaller than that 110 bytes. So I'm going to make an assumption that they're probably about 25 bytes per record now, and then a one-time payload of around 80 bytes for all of the common attributes. So if we were now to redo the pricing, what's going to happen is we have this 100 measures. This is going to fit into 3 writes, maybe about 25, 26, or 2.5, 2.6 kilobytes of data total. This would be 36 writes for the minute, and expanding this out, about 1.5 in a bit million writes for the month, and that corresponds to 78 cents. So if we were to just step back through this again here on what we have, if we were to send it all as a single shot, each record, one record at a time, it'd be $26 almost. If we batched it, it'd be $2.85. And if we were to combine batching plus common attributes, we'd be all the way down to 78 cents. So that's huge reduction in price, almost 2 orders of magnitude. So you can see that, that's how you're able to reduce data usage. So let's touch on to the memory and magnetic stores here. These are 2 storage layers. I talked a little bit about them, but what I'm going to touch on here is where you use each of these and why. So the in-memory tier here, this handles all ingested data. So data has to land within our in-memory tier. That means like if you have a record and the timestamp associated with that record was, say, 25 hours ago, and you configured the in-memory store for 24 hours, that data would be rejected. So the data does need to land within the in-memory store. I've talked a little bit about how the in-memory store handles the data deduplication, and how there's the semantics of first writer wins, or versioning that we have that does the last writer wins, in a way where you can specify a version and have that last writer semantics. The other thing is this in-memory tier, it's really designed around narrow queries. So these are the types of SQL queries that are hitting narrow points of time. Maybe you're asking for, hey, what happened in the last 15 minutes, or what happened in the last 2 hours, that sort of thing. And you're really kind of pulling out narrow slivers of data points. That's where those are the types of queries that this in-memory tier is really designed to give really good performance for. The magnetic disk tier, on the other hand, it's designed for analytics-like queries. So think of this as queries where maybe you're scanning through large periods of time, maybe even scanning through many terabytes of data, and you're doing month-over-month queries, that sort of thing. And it actually can even outperform our in-memory tier on those types of queries. And that's mainly because the way that we store data and the data structures in memory versus the way that we've laid data out on disk, very different, and they're optimized for these different types of queries. The other nice thing about the magnetic tier is that it's only 3 cents per gig per month, which is quite low cost. So you can store data in there for a really long period of time if necessary, and not have to, take it out of the system. It can be in there. We've had customers asking to have data in the magnetic tier, going back many years, and so we wanted to make sure we could fulfill that use case. So I'm just going to touch on some of the best practices here on data storage, ingestion. Obviously, if you can, batch records. You saw what that can do, or how much that can reduce pricing. It can also help with performance. Use the common attributes if possible as well. Again, it reduces the amount of data sent quite dramatically, and also does help with performance as well. You probably noticed that the dimension names, that there is a cost associated to them. Obviously, there is more data going across the line. It's more data for us to store. I reduced availability zone down to AZ. Obviously, you want to make them, as long as they need to be for readability and that sort of thing. Don't have to go too crazy or anything like that there. But yeah, obviously keep them as short or as long as they need to be. The last is configure the in-memory store here for the length of time that you have late arriving data. So if you have late arriving data that's arriving, 4 hours old, that sort of thing, you'll want to obviously configure that in-memory tier long enough to deal with that. But you'll want to keep it as short as you kind of need to based on your query patterns as well. So that'll be, there's a little bit of a balance there, but yeah, keep that as low as it needs to be, and understand that the magnetic tier really is high performing for those analytics queries. So let's go into the query processing side of things here. So Timestream is mostly ANSI SQL 2003 compatible. The one really kind of main one that you'll notice that if you're using it, is that we don't support table-to-table joins. So if you have multiple tables in Timestream and you're wanting to join those, that actually isn't supported. What we do syntactically support joins. So that would be like, you can do self-table joins. So if you have a single table and you're building up like a common table expression, and you have like these, these kind of like almost like subqueries, and you want to join those up together, we fully support the syntax for that. So it'd be like inner joins, outer joins, cross joins, all of that. So that's all there. The next thing is that the price of querying in Timestream, it's one cent per gig of data scanned, and that's the pricing of it. Most queries that from customers that I've worked with, most of the queries are scanning on the order of megabytes of data, and that's just the typical where you're querying kind of like the last 10 minutes or last hour, or that sort of thing. The querying side is done either through the SDK or the JDBC driver. So we have a JDBC driver, and you're able to use a lot of various tooling out there, whether it's open source tools like SQL Workbench or some of the partner and commercial offerings as well, where you're able to that support JDBC, and so you can use those. QuickSight has native support for Timestream. And lastly, Grafana is a very popular time series visualization tool, and we have full support for that as well, and that works with the open source version of Grafana. This is a typical query in Timestream. I'm just kind of going to walk through a handful of the things that we're usually looking for here. So the first thing is you're going to notice there's this predicate on measure name, which is CPU utilization in this particular case. Almost every query in Timestream is usually going to have a predicate on the measure, and this is because when you're working against a series of data points, you're going to typically be querying that measure name. The next is time. Obviously, being a time series databases, the vast majority of queries are going to have some sort of predicate on time, and we do make assumptions for that to be there. In this particular query here, this is just querying the last 2 hours. And then a lot of times queries are going to have predicates on a handful, maybe one, maybe two, or it could even be more of the dimensions. So in this particular case, there's a predicate on the host name. So just going over a handful of best practices. If there are predicates on those things like measure names and time and dimensions, those can reduce the amount of data scanned. So we will leverage those predicates to reduce that data, which obviously helps with performance, but it also does help with the amount of data scanned. Then we also, and I think this is usually makes sense, is if you are querying data in a database, queries like a select star can also cause for there to be more data read as well. So really only kind of query out the dimensions you need. So if you have, a really wide or large number of dimensions, maybe you have 20 dimensions in a table, and you're going to query some data out, you're probably only going to want to query, the ones you really need. And so don't query out unnecessary columns or dimensions, I guess, is what they'd be in Timestream. So just query out what you need, and that'll also can reduce the data scanned and also improve performance. Lastly, and this one's kind of a little bit of a special case one where it comes in, and it may not apply to all queries, is group bys. If you are grouping, you have a set of dimensions you're grouping by, and if for some reason you do, you have a choice on which way you can order those columns. If you're able to put the higher cardinality, or the one with a larger number of unique values first, that actually does help with performance in Timestream. So if there is a choice there, ordering it out with the higher cardinality first in the group by will improve performance. So as I said, I'm going to give you guys some additional resources here. This is a screenshot off of the Timestream console. We also have these same videos. They're up on the Timestream main Timestream page. There's a tutorial in here. There's a getting started, which goes deeper into things like the measures and dimensions and explaining that sort of thing. And so if you're looking for kind of more introductory session, that'll be helpful. If you're looking to do an integration with IoT Core or Apache Flink or Grafana or QuickSight, those videos are there, not shown on this screenshot. We also have a video for working with SageMaker as well. So you can check these videos out for additional resources. And lastly, these are the links on GitHub where you'll find various samples. We have sample applications on how you can kind of configure and use Timestream in a bunch of different development languages. With the first one with that sample apps, and then the rest of them are really kind of what I was talking about earlier with it, which we have the videos that correspond to using things like Apache Flink and IoT Core and that sort of thing, and you'll find the code examples for those here on GitHub. Thank you very much for tuning in for this session. Please don't forget to fill in the survey after.